right, shall we get started?
Sounds good.
All right. Well, welcome everybody. So this is a joint lecture. So welcome everyone from. I guess I invited all my classes, but primarily this is the time slot for EGME 417, and also welcome to Dr. Sanders' EGME 430 class. So you know, maybe this has been hyped up to this point, but today what I'm going to be talking about. Oh, I'm Dr. Tran, by the way. My name's on the slide. And today what I'm going to be talking about is just some of the past research that I've done on kind of applying fluid mechanics and simulation technology kind of more generally to study blood flow. So it's a kind of a biomedical you know, application that, you know, I think, you know, a lot of people we don't really see in our core curriculum. So does everyone see the full screen of my slides right now, or is it or does it look weird?
Yep, I can see it.
Okay. So before we begin, you know, usually I like to keep my seminars pretty informal. So at any point, I'm just going to keep trudging along, and I'll stop every now and then for questions. But if you ever have any questions about any slides, just, you know, turn on your mic and just feel free to interrupt me, and I'm always happy to answer any questions. Okay. So this is the title of my talk. So it's computational modeling of blood flow. Okay. So let's jump in. So let's start with just some background information. So you know, the first thing I think where I like to start is just talking about just your cardiovascular system in general. So hopefully this kind of brings back some memories from high school biology. Okay. So your cardiovascular system, you know, when I say that, I kind of refer mostly to just the kind of your heart and kind of the vast network of all the blood vessels in your body. So what I've found here was an image that I found on Google of a person where all his skin and bones are gone, and you just see his blood vessels. But at least he's happy, he's waving. Okay? So the main responsibility for your cardiovascular system is to transport oxygen and nutrients to your body. You know, specifically just for oxygen, you know, the way that all your cells in your body get oxygen, you breathe it in through the lungs, your blood vessels pass through that, and it takes that oxygen through the rest of your body so that your muscles can move, and all your other organs can perform their duties. And the same thing goes for the nutrients that you eat from your food. Okay? So I think everyone knows this, but you know, proper maintenance of the cardiovascular system through regular diet and exercise, it's very vital to your overall health. I think, you know, a lot of people when their health starts to fail, a lot of times it's due to the cardiovascular system. So it's something that you need to regularly maintain with, you know, a good balanced diet and just regular exercise, so your heart gets, you know, some good workout every now and then. Right? And it's, you know, this fact I think down here is really surprising, where, you know, there's, you know, even though we think of ourselves as just kind of a single person, but if you took all the blood vessels in your body and you kind of laid them end to end, you know, you'd have a lot of blood vessels in your body. So the people have estimated, or scientists have estimated, that there are about 60,000 miles or 100,000 kilometers of blood vessels in your entire body. So it's, you know, even this picture I'm showing right here doesn't really do it justice, because you're really just a really dense pack of blood vessels that go throughout your body. Okay, so a lot of my research is focused on, you know, studying cardiovascular disease. So, you know, as kind of the name suggests, you know, these are kind of diseases or pathologies that negatively affect your cardiovascular system. So, so what I have here are some statistics. So they're a bit outdated. So I think these are from 2010. So these are the statistics that I used when I was going through grad school. And of course, this has been updated by now. But just, you know, just by looking at these statistics, you can get a sense of, you know, how much of an issue this is, and how much, you know, we want to improve this. Okay? So just in the cost of life, you know, cardiovascular disease, it's still, you know, the leading cause of death worldwide. So about 17 million deaths annually occur due to cardiovascular disease, and about 600,000 of these occur in the US. So it's not only the cost of life, but also financial costs are also substantial. So it's been estimated that treating cardiovascular disease costs the US about $500 billion. You know, and that's not only with hospitalization costs, but also just in the cost of lost productivity. Because, you know, if someone has to stay in the hospital, or if someone has to stay home to nurse their cardiovascular disease, they're not working and they're not producing, you know, income for themselves or for their families. And, you know, this cost is only expected to go up with time. You know, what's generally expected is that, you know, in order for us to kind of improve these numbers and to kind of improve the cardiovascular health of our nation and around the world, we need to better understand disease mechanisms so that we can develop better treatments and improve these outcomes. Okay, so what are some of these challenges? So before I kind of go into these challenges, I just want to say that up until maybe within the last 10, 15 years, the cardiovascular disease and just biomedical in general has been kind of the realm of like medicine and biology, and they've made tremendous strides in what they can do in terms of treatment and research. But even then, there's still a lot of improvement that can be made. And this kind of goes across the board in terms of like drug therapies, better operating procedures, better hospital conditions. But the challenges that I kind of want to focus on, and the ones that I'm more interested in tackling, is with the idea of measurement and observation. So if you kind of compare the cardiovascular system in a human body with your typical engineering system, like a car or a building or an airplane, it's really hard to get good observations and good measurements, because you can look at yourself just sitting here right now, so you don't really have any blood vessels that are kind of exposed to air. So if you wanted to measure things like the velocity of the blood, or even blood pressure can be tricky to measure. A lot of times this involves a visit to a clinic. So you have to go to the hospital and they have to stick some probes inside you, and it's an uncomfortable procedure, and you have to pay like $2,000 for it, and it's not good. So a lot of what we don't know about the cardiovascular system kind of stems from the fact that we just don't really measure it all that much. And without constant data, it really makes advancement really challenging. So then now we can start to ask, as engineers, how can we help? So we're as engineers, specifically as aerospace engineers, we've already developed technology that can simulate fluid flow. So in particular, in the aerospace industry, we've developed this tool called computational fluid dynamics, and it was kind of developed with the intent of helping to develop airplanes and rockets without doing costly experiments. So everyone knows that building an airplane and building a rocket is extremely expensive. And if you want to try out and kind of iterate on different designs, you're not going to be building a new airfoil, and you're not going to be building a new rocket ship every time you want to test something new. So computational fluid dynamics kind of came about as a way for scientists and researchers to develop these new designs at a very, very low cost. Since we already have that technology, it kind of makes sense that we kind of apply that same technology to other fields as well. So not only aerospace. So luckily for me, blood is it's a fluid just like air. So why don't we just use the exact same technology that we use for computational fluid dynamics and use it to simulate blood flow? And with that, we kind of get around a lot of those challenges that I talked about earlier, where with the simulation, you don't have to worry about like sticking invasive probes into people, because you can just simulate everything, and you can just, from that simulation, you can get all the data that you need, at the convenience of just sitting in front of your computer. Right? So how do we do this? So what I've shown right here is just kind of the general workflow that I've typically followed. So I'll say that this isn't the only one, but this kind of methodology that I'm going to tell you is called patient-specific cardiovascular modeling, and the key word here being patient-specific. So when we're building these computational models, like for the simulation that I'm showing here on this page, the anatomy for this and the geometry for this is extracted from a real person. So the idea with this kind of technology is that if you have some kind of, if there's some kind of suspicion that you might be under some, cardiovascular risk factors, you can go in and get like a simulation that's tailor-made to you, and we can use that to help, diagnose your disease. So the starting point for this kind of simulation is going to be some kind of medical image data. So that's what I've shown you here on the left. Right? So medical images, I think a lot of people are familiar with X-rays. So people get X-rays all the time to view their bones. So another kind of form of medical imaging could be a CT scan or an MRI. So these kinds of scans are really, they're a bit different than the typical X-ray, because the X-ray will show you your bones. But with these kinds of scans, what they'll highlight instead of your bones is they'll highlight your blood vessels. And kind of the way that they usually do it is they expose you to some radiation, although it's a very safe amount, and then they'll inject some dye into you. And the dye is usually very safe. It doesn't interact with your body at all. What that dye does, it kind of helps to highlight the different the different vessels in your body, so that we can get kind of a really good picture of it. And then from this medical image data, what we do is we load it into our program. So our program is called SimVascular. which is free, by the way. So I'll kind of use this to give a shameless plug for the software that I worked on in grad school. So if you go to www.simvascular.org, you can actually download this software and actually try this out for yourself and run CFD simulations on your own laptop from medical image data. So once you've obtained the medical image data, the first step is to trace out what we call the path lines. So the path lines, they're basically the centerline paths for all the vessels of interest. So this is actually, even though this is the second step, this is probably the most important step in your modeling, because what you'll see is that if you load up any kind of medical image data, and considering the fact that you have 60,000 miles of vessels in your body, there's tons and tons of vessels in there that you can possibly model. So you want to identify basically just the most important ones that you're interested in modeling. And getting that information is difficult because a lot of times those are driven by the clinical questions. So a lot of times you have to be in constant kind of communication with the doctors to kind of pick out what are the most important vessels that you should do. So then once we do the path lines, the next step is segmentation. So basically what we need to do here is we're going to follow the path lines along, and we're going to basically trace out the cross-sectional area. As you can see, just because we define the center lines, it doesn't really give us enough information to build a model. So we need to define both the shape and the area of the cross-sectional vessel. And so this image that I have here is actually a really good example, because you can see that we have some vessels here, like this one in the middle, that's extremely large. So they have a very large cross-sectional area. And their cross-section it's roughly circular. But then right next to it, you also have vessels here that have a very small cross-section. And it's a bit tough to see, but these cross-sectional areas here, they're not perfectly circular. So a lot of them might be ellipses, they might be semi-moon shaped, and you want to really get those shapes really well and accurate if you're going to do a simulation on this. So the next step after the segmentation is called lofting. So I call this step 3D connect the dots. So I usually my collaborators, they hate it when I say that, but that's kind of what makes sense to me. Because what you're doing basically is you're taking all your segmentations here and you're connecting them. You're basically connecting them together to form kind of a solid body in order for you to run simulation. Okay, so the next step after that is the mesh. So for those of you who are visiting from 417 and 410, you should be very familiar with this step. Before we can run a computational simulation, we have to discretize our domain. So we have to basically, replace it with a bunch of simpler shapes so that we can form our equations on it. So then after we do the mesh, we have to apply our boundary conditions. So boundary conditions are going to be really important. So I'll kind of get more into that later. But the boundary conditions, as you'll see, have a big impact on the results. Right? And then once you have the boundary conditions, you can pass this to a supercomputer, and the supercomputer will run your simulation, and then you can get your results. So I have two different results here. So on the left here, I have pressure, which is kind of a first result that people typically look at. Now on the right here, what I've shown are the path lines. So you can see, I've kind of filled this model with a lot of dental floss, and those dental flosses basically trace out the path of a fluid particle that goes throughout the simulation. Right? Are there any questions at this point of the presentation?
How do you get your cross-sectional areas of the blood vessels? Like, is it a measurement that's just widely known, or is it just an assumed number?
Yeah, that's a great question. So the segmentation is actually mostly done manually. So you need some specialized software for it. So you need specialized software to basically load the medical image data. And then once you draw the path lines, what you can do is you can kind of ride along that path line, and it'll show you kind of a 2D image of what that medical image data is at that point. So what you typically do there is you kind of use your mouse and you kind of draw out manually what the cross section looks like. So I say it's manual, which is I think is surprising for a lot of people, because it's if you look at kind of this medical image here, you can kind of clearly see that all the kind of the bright white parts, those are clearly blood vessels. So if the cross section is kind of clear enough, there are some automated tools that you can use to kind of automatically draw that segmentation. But a lot of times you're interested in kind of vessels that are on the fringes here. So you can kind of see all these little white specks. So with those vessels, it's really hard for the automatic tool to kind of pick up on that image data. So you kind of have to use your own intuition, and you kind of have to use your own judgment to kind of draw out those cross sections. So for a lot of these smaller vessels, when I made this model, I drew basically all these smaller ones by hand, just because it was really hard for the image data to pick it up.
How did you decide on how many segments to do?
Yeah, that's a great question. So basically that's usually up to the operator, how many segmentations you do. And that kind of leads to some kind of skepticism because everyone kind of does this a little bit differently. But kind of the method that I use is that if it's, I try to pack a lot of segmentations close to each other if I see that the cross-sectional shape and cross-sectional area are changing very rapidly. So you can see right here, you know, I've kind of very densely packed these segmentations here because I saw that the cross-sectional area was changing a lot. And you can kind of see that on the model right here, where like you kind of have this kind of jaggedy part. But for sections of the vessel where the cross-section is not changing all that much, you don't really need to put too many segmentations in there. So it kind of saves you a little bit of work. So for this kind of segment of the vessel right here, you can see it's mostly straight. So what I saw there was that the cross-section wasn't really changing that much. So I didn't really, I didn't put too many segmentations in there just to kind of save some work because it wouldn't have added too much detail to the model.
How critical would that be? Like if you're like simulating someone's particular flow, how critical would it be to have the shape have like a high accuracy or fidelity as opposed to like being able to just kind of eye it based off of maybe a couple pictures or something like that? Would that be endangering, or would that be like, I don't know?
Yeah, no, that's an excellent question. So right now, kind of the state of the technology is no one really knows for sure. So this technology, as you can imagine, is kind of still in its relative infancy. So a lot of the technology is kind of being built, you know, still kind of, you know, from the ground up right now. So kind of where we're at right now as kind of a field is that, you know, doctors basically are asked, that's usually the very first thing that they ask too. And right now, you know, we can't really give them a great answer because it's, you know, we don't know because there's just not enough data. And I think part of the challenge is that because all these models are patient specific, they're specific to the patient. It's really hard to kind of get statistical significance across a lot of different patients, especially because these models are usually very time consuming to make. So like this one in particular took me about a week of just sitting at my computer for like 8 hours a day, kind of just modeling this thing. So it's really hard to kind of develop enough of these to really know what are the crucial things. Of course, you know, we have our own kind of, you know, just personal intuition. Because a lot of times when we run these simulations, we're interested in kind of a specific area of the model. So like say that we know that there's disease in this vessel right here. So we know that we want to really be careful with our segmentations here and be really careful. But for some other parts of the model where we're not, you know, specifically that worried about, we can be a little bit lax in those areas because they're not going to really affect things that are local to this area right here. So it's actually kind of very similar to, you know, how we decide mesh refinement in 410. Because a lot of times you want to really pay attention to the areas where you really want to pay attention to, and the other ones you can be a bit more relaxed. But to kind of answer your question more directly, there's no rigorous guidelines right now because it's still, people are still kind of trying to figure this out. Yeah.
Okay, thank you.
Mm-hmm. Okay. So what I've just shown you is kind of the methodology to produce kind of the three-dimensional model. But as you can imagine, if you kind of remember from the beginning, you have 60,000 miles of blood vessels in your body. So, you know, to basically do this process for 60,000 miles of vessels at the moment is just not practical. So a lot of times what we have to do is we kind of have to focus our 3D modeling on just kind of the areas that we're mostly interested in. And then for all the other parts of our vasculature, you know, all the blood vessels in our arms and our legs, you know, that aren't directly in our 3D model, we have to kind of approximate their behavior. And so the way that we do that is we use a method called lump parameter modeling, where we basically use an analogy in between fluid mechanics and circuits, believe it or not. And so what you can do is you can basically take all the blood vessels that are downstream of your model and basically model them with like resistors and capacitors and inductors. You know, that I'm sure was everyone's favorite class here at Cal State Fullerton. So, and so kind of the analogy that we make is that once we kind of replace these vessels with these elements like resistors, capacitors, what we say is that when we compute the voltage in these circuits, that's basically the same as fluid pressure. And when we compute the current, that's essentially the same as the fluid flow rate. And so this kind of methodology will really help us to kind of cut down the cost of our simulation, which is, you know, anyone that does kind of simulation work knows that cost is always something that's on your mind. Okay, so let's talk governing equations. So, so since blood is a fluid, just like air, it follows the Navier-Stokes equations. So the, you know, for those, just a reminder from 333, your Navier-Stokes equations are going to define the conservation of mass and momentum for your fluids. Okay? And so, you know, if you kind of remember from 333, a term that you might have heard from back then was a Newtonian fluid. So a Newtonian fluid basically means that the shear stress in the fluid is basically proportional to the velocity gradient. So even though blood is typically not a Newtonian fluid, it's actually one of the most famous non-Newtonian ones. For the purposes of the simulation, just to kind of make our computations a bit more simple, we assume that it's a Newtonian fluid, so it kind of follows the classical Navier-Stokes. And we kind of justify that assumption by saying that, you know, the shear thinning behavior, which is the non-Newtonian behavior that blood experiences, you only really observe that at really small length scales. And kind of the reason for that is, you know, when blood has to kind of squeeze through your tiny capillaries, you know, and your blood is basically comprised of a lot of tiny blood cells. So the blood cells kind of have to squeeze their way into the capillaries, and that's kind of what gives rise to the shear thinning behavior. But when you're in kind of the bigger vessels, like the greater vessels in your body, you know, you basically don't see the blood cells. You basically assume that the blood is kind of just a continuum fluid. So in that case, you know, we assume it's Newtonian. And there are a lot of experimental measurements that kind of back this up too. So, you know, for the big vessels, we assume it's Newtonian. So here are your governing equations. So I have the conservation of momentum. So you have your unsteady term, you have your convective term, you have your viscous term, which is the diffusion of momentum, and then you have your pressure term here. And then down here you have your conservation of mass, which is given by just the divergence of velocity. So by this, we're assuming that our fluid is incompressible. Okay, so that's the governing equations. But in order to actually simulate this, we need a method to discretize it. So for 417, you know, we've used the finite difference method and finite volume, and in 410 we use the finite element. So the method that I typically use for my simulation is actually finite element. And kind of the reason for this is that finite element methods kind of really shine for applications where the geometry is very complex and awkward. And anytime you're kind of dealing with very patient-specific geometries, you're not going to be dealing with very nice cylinders or very nice squares or rectangles. So you really need something that can really adapt to that geometry. And the finite element methodology really helps us out for that. So I'm not going to get into the math of finite elements. So for 410, you know, we've spent basically an entire semester doing that. But basically the upside is that, you know, through the finite element method, we take a partial differential equation, which is the Navier-Stokes equations here, and we turn that into a system of algebraic equations that we're going to solve on our mesh. Okay? And the nice thing about algebraic equations is that there are a lot of methods that computers know to solve these methods. So if we can get our PDE into that form, then the computer will have a much easier time to simulate that. Okay, so let's talk boundary conditions. So, you know, anytime you do any kind of simulation work, boundary conditions are extremely important. Because, you know, we know that the Navier-Stokes is going to describe how our solution behaves on the interior, but we also need to define how the solution behaves at the boundary. Okay? So if you're in 417 and 410, you should be familiar with the term Dirichlet boundary. So a Dirichlet boundary condition are types of boundary conditions where you directly specify your solution variable. So if we're solving the equations of fluid mechanics, our solution variable is going to be velocity. So a Dirichlet boundary condition will be any kind of boundary condition that supplies the velocity of our solution. So in blood flow simulation, this kind of takes two different forms. So we can either directly supply the velocity itself, or another popular form is that we can directly specify the mass flow rate. So in 410, you know, that's kind of what we did on Tuesday when we did Fluent. Okay? So these kinds of boundary conditions, they're very common for inflows, because then we can kind of define how much mass, we can easily define how much mass enters our domain. Okay, so another type of boundary condition that we can have is a Neumann boundary condition. So these are the same as natural boundary conditions. So for fluid mechanics simulations, the Neumann boundary conditions are going to be stress. So stress basically relates to you know, how much force that a fluid represents. Okay? So pressure boundary conditions are very common at the outputs or the outlets, from where you can define kind of what's called the back pressure. That's kind of defining your model. Okay, so those are the two kind of standard boundary conditions. So if you're doing any kind of computational fluid dynamics, either within like an aerospace context or blood flow, Those are kind of the ones that are kind of always in your toolbox. But because blood flow is kind of very unique compared to those other types of situations, we've developed kind of our own kind of very specialized boundary conditions. So the first kind of boundary condition I call it like an outlet resistance. So this kind of goes back to how when we were talking about our lump parameter boundary condition, or lump parameter methods, where we kind of make the analogy between fluid mechanics and circuits. Okay? So specifically for blood flow simulations, what you want to model like your outlets usually is the effect of all the downstream vessels that you don't see in your model. So these are like all the tiny capillaries that you weren't able to create in your 3D model. And so kind of the most important effect of those capillaries is kind of their viscous resistance to flow. That's kind of contributing to your pressure. So the way that we can kind of capture this is with an outlet resistance. So instead of just directly specifying a constant pressure at our outlets, what we can say is we can supply a pressure boundary condition, but this pressure is going to be proportional to the amount of flow that comes out. So we basically have this formula right here. Pressure is equal to Q times R. So what we can do is we can compute the amount of flow that comes out, multiply it by some resistance, where this resistance is determined by the by all the downstream vasculature, so all the capillaries that are downstream. And then through this product, we can compute a pressure, and then this pressure is the one that we can actually apply as a boundary condition to our model. So what we've found through our research is that this provides a much more accurate kind of simulation of blood flow than kind of just a straight up pressure, because then this pressure is kind of more adaptive to how much flow is going through. And this concept of resistance is something that's it's a concept that clinicians actually often use, because it's you know, a lot of times when someone has high blood pressure, another way that clinicians usually think about it is that all their little capillaries, they're constricted, so they're going to have high resistance. So this idea of like resistance of like your capillaries and your downstream vessels is something that kind of very naturally kind of goes with how clinicians usually think about these things. Okay, so another type of boundary condition is called the Win-Kessel. And so this is a kind of a more advanced circuit. So instead of just a simple resistor for your outlet, what you're including now is a capacitor and a second resistance. And so kind of the big addition here is this capacitor. And so what the capacitor will allow you to model is the fact that your blood vessels are not rigid tubes. So your blood vessels, you know, they're basically flexible. So they're basically going to expand and contract in response to blood flow. And so to kind of capture that behavior in the downstream vessels, what you can add is a capacitor. Okay? And so as you can imagine, since we're adding additional physics here, we're going to get a solution that's more accurate. But you know, because we're adding more components, it's going to be computationally more challenging. So you know, it's a little bit more difficult to implement, and it takes a little bit longer to solve. But a lot of times, it really gives you a much better result. Okay, so those are all the boundary conditions, or the typical boundary conditions that you can have for the inlets and the outlets. But we haven't talked about the walls yet. So you know, you have when you have your 3D model, you have the lateral walls of your blood vessels. So those guys need boundary conditions too. So the first condition that I'll go over is called the rigid wall boundary condition. So the rigid wall boundary conditions, we basically assume that the blood is not going to slip at the wall. And so what that essentially means is that we're going to assume that the velocity goes to 0 at your solid surface. Okay? And the reason we call this a rigid wall assumption is because, you know, if the velocity is 0 at the wall, then the wall itself isn't moving. So we're basically assuming that your blood vessels are made of steel. And then when you're pumping blood through there, the wall doesn't react at all. So of course, you know, this is not realistic because your blood vessels are flexible. If they weren't flexible, you couldn't move your arms like this. You know, you'd have literally steel pipes in your arms. But you know, this is usually a very simple kind of first approximation. So this is, you know, the reason we use this in the simulations is because it's really simple to kind of implement. It's really simple to get a simulation off the ground with a no-slip boundary condition. Okay. But what's more accurate is if you run a deformable wall simulation. And so what you do in these kind of simulations is that you basically assume that your walls can be flexible. And so the way that you actually solve these problems is that you include kind of the equations for solid mechanics into your vessel wall. So you're kind of solving both the fluid equations and the solid equations at the same time. And then those two domains are basically going to be interacting with each other. So this kind of methodology is known as fluid structure interaction, or FSI. That might be a term that you might come across in the literature or reading up on this. Okay. As you can imagine, this leads to much more accurate simulation. So you know, just by looking at this animation here, you can see that looks a lot more natural. than something that's just a rigid tube. But kind of like as what we said before, the more physics that you add to the equation, the more computationally expensive it's going to be. And actually, this will be kind of a subject of my talk, which it's near the end, so I'll try to kind of get there. But there are a lot of different methods that you can use to actually simulate this. Okay, so are there any questions on the boundary conditions or anything that we've covered so far?
Yeah, I had one.
Sure.
Kind of a two-part thing. The second part's based on the first part response. So,
okay.
At the scale that you're dealing with to view blood as being a Newtonian fluid, are you also assuming that it's isotropic?
Yeah, that's a great question. So yeah, we are assuming that the blood is isotropic. So we're only specifying a single viscosity and a single density.
Okay, so for that, just because you have the independent materials properties, number 2 for those, and your viscosity coefficients are partially based on density, does that mean that rho is an average of densities between the plasma and the blood cell density itself?
Yeah, that's a great observation. So yeah, the density is basically going to be an average of those two things. So we don't separate the cells and the plasma. So we assume kind of just an aggregate density between the two.
Thanks.
Any other questions on this before I move on? Okay. So I also have a slide to kind of talk about the time advancement. So I think in 410 we didn't really get to this, but we talked about this a lot in 417. So we know that whenever we have an unsteady problem, we know that we have to advance this forward in time. So in 417 we kind of went over the basic methods called the explicit Euler and implicit Euler. So in the simulations that I ran, I used kind of a hybrid between the two. So the method is called the generalized alpha method. And you kind of think of it as kind of a hybrid in between explicit and implicit Euler. So it kind of takes the best of both worlds and kind of packs it all into one package. Yeah. So I won't go too much into it, but you can kind of think of it like that. Okay, so now let's talk output. So now that we've kind of established the kind of the methodology of how we run these simulations, now the question is, what can we get out of this, and what what outputs are actually useful to clinicians. Right? So the first thing that you can typically look at is the flow. So we know that when we solve the Navier-Stokes equations, we get the velocity field, and then from that velocity field we can compute the flow rate. So flow rate is something that's really interesting, especially when you have a system with a lot of branching paths like this. So a lot of times what you're interested in is how much blood is going to this specific area. So if we're kind of running a simulation of our torso, we can basically determine how much blood is going to our arms, how much is going to our head, how much is going to our legs, right? And that's something that can be really useful information for a doctor can use to basically design some treatment. Okay, so another output that's interesting is pressure. So actually pressure, I think is one of the really primary ones that people look at. So everyone knows that about blood pressure. So blood pressure, is kind of an indicator of your overall health. So if you have high blood pressure, that can be really bad. But that kind of describes your overall blood pressure that you can measure kind of from your arm. But even just local pockets of blood pressure are also really interesting to view. And with a simulation tool like this, you can really get a good kind of picture of how pressure is distributed throughout your blood vessels. So what I'm showing you at the top right here is actually one thing that they actually use a lot in the clinic. So what they're measuring here is called FFR. So that stands for fractional flow reserve. And what they use this for is they actually use it to measure kind of the severity of disease. Because what happens a lot, especially in older people, is that they have kind of constrictions in their blood vessel. A lot of these are through diet, but these can form for other reasons too. But a lot of these constrictions are, believe it or not, are actually not all of them are actually dangerous to your health. Because what actually determines whether a blockage is significant is if it's actually impeding blood flow. So you can have a narrowing here, but if it's not actually impeding blood flow, then it's actually safer to actually just leave it alone. And so a lot of times, when doctors, they take like an x-ray or they take a CT scan of a person, they usually see a lot of these kind of blockages in the body. But if they actually try to react to every one of these and try to treat every single one, especially with surgery, that can actually be more dangerous for the patient. So actually what they do in order to measure how severe a blockage is is what they'll do is that they'll take a pressure probe. So they'll basically stick a probe up your groin, and then they'll snake it around to the part of the body where the blockage is. And what they'll do is that they'll measure the pressure drop. So they'll take their pressure probe and they'll measure the pressure kind of proximal to your blockage, so on the upstream side. And then they'll measure the pressure on the downstream side, and then they'll compare the two results. And so if this fraction is pretty small, so I think the threshold is like 0.7, so you have basically a 30% pressure drop, then that's something that they can say, okay, this is something that's significant, and we should either treat this with medicine or we should treat it with surgery. And so, this is, even though I just described this procedure, it's not something that everyone wants to get every day, because no one wants to stick a wire up their groin and snake that around to your heart. And so there's actually a company out there called HeartFlow that I actually have several friends at, where they actually use simulations to measure this FFR. So you can get like a clinical grade diagnosis without actually having to go into the hospital and stick a wire up your groin, which obviously is something that's really attractive to people, because it's not only is it going to be a lot more pleasant because you don't have to you don't have to stick something up your groin, which is never fun, but it's also going to be a lot cheaper for you because you don't have to pay for hospitalization fees. You basically get a scan, you send it to an engineering company, and then within like a couple hours you have your results on whether you need to get surgery or not. So so the pressure field that you get from simulations basically allows you to do this. Okay, so another output of interest is called the wall shear stress, right? So this one's actually another one of the big ones. So I'd say after pressure, this is something that people can measure. Okay? And so because we assume that the blood is a viscous fluid, it's going to impart some kind of viscous shear stress on your vessel wall. Okay? And so this viscous shear stress is actually really important for your body, because your blood vessels, they're not just rubber tubes in your body. They're actually lined with actually living cells, and those cells will actually respond to some of the stresses that they experience. And so measuring this wall shear stress, this kind of is one piece of the puzzle to kind of of predicting how your endothelial cells will react to blood flow. And the reason this is so significant for simulations is that this is extremely difficult to measure, in a person in general, because this is basically the viscous force that's like right up at the surface of your blood vessel. So it's hard enough just to measure pressure by sticking a wire up there, but to measure something that's like on the walls of your blood vessels is extremely difficult. So there's kind of a lot of new research that's kind of being born of this simulation technology, because we can simulate wall shear stress a lot more easily than people can measure. And so from this, people are researching different disease pathways and cell mutations and stuff like that. So, just being able to simulate the wall shear stress and use this in disease research is something that's really exciting. Okay, so another output of interest is known as residence time. So residence time, what I mean by that is kind of the amount of time that blood kind of stays in one spot. So ideally what you want in your system is you want your blood to be kind of circulating all throughout. So you want your blood to kind of go through your body, deliver what it needs to, and then come back to the heart so it can kind of recharge and get all the oxygen and nutrients that it needs. But this doesn't happen all the time, because what can happen sometimes is you can have kind of local pockets like this. If you kind of have like an internal tear in your blood vessel, and you can have kind of a pocket right here where blood kind of just stagnates. So stagnation of blood is something that's really bad, usually, because what that means is that this blood is not, it's not getting all the oxygen and nutrients it needs to supply this blood vessel with the things that it needs, but also because whenever you have stagnant blood, the blood tends to clot. So kind of the term that we use for that is called coagulation. So if you can, if you kind of think back to your playground days where you scrape your knee and you have blood that's gushing from your knee, and it's disgusting, and you gross out all your friends, that if you kind of held that enough and the blood kind of stays there, and you kind of force that blood to stay in one place, the blood will clot. It'll kind of form a solid surface from which your body can heal. So blood clotting is great for healing wounds, but you don't want your blood to clot in the middle of your blood vessel, because that'll cause a blockage, and that's really bad. And so from simulations, we can compute what's called this residence time. So we can compute, how long the blood can stay in, how long the blood is staying in one spot. So we can actually go in and do an intervention if we need to. Okay, and so another output that we can look at is known as the wall strain. So if you run a deformable wall simulation, you can basically measure the structural stresses in your wall. And so this is also something that can be really interesting because this determines how the the cells that line your vessel wall, how they're going to respond to that stress. So if you run a deformable wall simulation, this is also something that you can do. And it's also something that's extremely difficult to measure, in a living person. Okay, so before I jump into kind of my own specific research projects, I want to talk about some applications. So kind of the first application that I've been talking about is disease research, right? And so because, these simulations kind of give clinicians and give engineers kind of a wealth of new data that's not normally, or that's really difficult to obtain in living people, we can use that data to kind of study, how does this disease progress? What's kind of the trigger mechanism? So there's a lot of research into like aneurysms. So aneurysms, you might have heard the term from memes, but the kind of the technical term for an aneurysm is just a sac of blood that kind of forms in your blood vessels. That's usually not wanted there. So for many years, it's kind of it's kind of a mystified clinical research because they don't really know exactly why aneurysms form. Partially because we're not looking at people's blood vessels all the time. So there's a lot of research going on right now is how can we use these simulations to kind of predict if an aneurysm will form, so we can actually go in and do something about it before it gets to a dangerous spot. Because a lot of times by the time an aneurysm actually forms, sometimes it's kind of too late to actually do something. You kind of have to do like a really dangerous surgery, especially if you have an aneurysm that formed in your brain. So I don't watch Game of Thrones, but I know that one of the actresses in Game of Thrones actually had an aneurysm in her brain. And thankfully, I think she was able to recover. But a lot of people, they kind of get those in their, and they don't really recover that. And so the hope is that the simulation technology can actually predict that and kind of help doctors can go in and actually do something about it sooner rather than too late. And we've talked about HeartFlow. So HeartFlow is kind of that company that measures fractional flow reserve to measure basically coronary artery disease. Okay, so another application could be medical device design. So just like we use FEA to design like our cars and our engine parts and stuff like that, we can use the same kind of technology to design medical devices. And so this obviously is very attractive to the bioengineering companies, so like Edwards Lifescience or Medtronic, because this gives them a way to kind of iterate and try out different designs without having to actually run an expensive experiment. So you can basically simulate these and basically figure out how it's going to work before you actually put it, well, first of all, before you put it into a human, that there's usually a lot of steps before that, but before you even design like an experimental setup. So this can save you a lot of time and a lot of money. And so another really interesting application is you can actually perform virtual surgery. So you can basically take this virtual platform and you can try some surgical procedures on it without any risk of human life. So I'll tell you a story related to this, and I think I'll remember this for the rest of my life. When I was in grad school, I talked to a surgeon. He worked at the hospital, and he's relatively well known because he's known for kind of developing this specific surgery around kind of one of the valves in your heart. So I just asked him, I said, I never would have thought to do the thing that you did. So how did you figure out how to do this? It must have come from a lot of training, a lot of intuition, a lot of things that you know about the human body. And he looked at me and he said, honestly, what happened was that I was working the surgical suite, and someone came in and they had this condition and nobody knew what to do, so I just tried something random and it worked, so now I'm famous for it. And that's good. That's literally what he said to me. So I was beyond shocked, because this is someone that we're putting a lot of people's lives in the hands of, and to say that he didn't say that it was completely random. He said he basically tried something, and he basically said if it worked, I was going to be famous, but if not, then it's then that's that's not good. So obviously we can't do that nowadays. So we've kind of the health field has kind of advanced to a point where the only thing that we actually try in live humans are going to be things that we know are totally safe, and kind of contributing to that is the fact that we have all these virtual tools now, or we can try new surgeries without putting real people at risk. And then beyond that, we can actually do even some more stuff. So once we have a surgical procedure, we can actually treat it like a design optimization problem, and we can actually optimize these surgeries. So actually, one of my good friends in grad school, he worked on this. So he was a big optimization guy, and what he did was he worked to optimize these surgical procedures. Okay, So any questions on these kind of applications and kind of the outputs of these simulations?
I have a question on like the different considerations and parameters that you might need to take, because
Sure.
I mean, I know that with these, the applications are from what you were talking about before, a lot of them are like kind of fluids and stuff like that, with blood, treating blood as a fluid. But like you mentioned before, you guys have like the cell walls that are living tissue that respond to shear stresses. And I'm sure even the blood vessels themselves probably respond to stresses a certain way. Wouldn't those have not just like an engineering structural effect on the surroundings, but like, do you guys have to consider like biological effects that those shear stresses might have, like hormones that might be released or things that might happen to the cells themselves?
Oh yeah, absolutely. Yeah. So yeah, you kind of hit the nail on the head. So these blood vessels, even though, when we're simulating these, we're kind of implicitly assuming that they're kind of I would say like a biologically inert system. So they're not going to basically react to what we're doing and the flow that we're putting in. But that's like you pointed out, like that's absolutely not true. So over time, like these cells, they are going to react. They're going to release hormones. They're going to, change and evolve and grow, as a result of the blood flow. And I'd say that, right now there's a ton of research going on into saying how can we actually account for this. So the difficult thing is with biological systems, you're dealing with the system that's extremely complex. So even just the purely physical side of just doing the fluid mechanics, that's already really difficult, with the geometry and the boundary conditions that we have to do. But there's a whole other can of beans that we haven't opened yet, which is the biological side, and seeing how things are going. So I can't comment on the hormone stuff because I'm not really familiar with, but I do know that there's research into having these blood vessels kind of grow and react over time to the blood. So that kind of research is known as growth and remodeling. And so, over time, what can happen is these blood vessels, they can either grow or they can either shrink, as a result of the blood flow. So the problem with that is that the timescales for those effects, the fact that, or the amount of time it takes for a blood vessel to kind of grow an extra layer, or for it to kind of shrink a little bit, that occurs over the orders of like days and weeks and months. So, your blood vessels, they're not going to suddenly, grow and close on you, right? Because, it's, even if you have kind of a really bad diet, it takes a long time for that to take an effect. And so the problem with that is that when we're running the simulations, we're simulating these, and often we have to use time steps such that, the amount of time that we have for the simulations on the order of seconds. So, you can run a simulation for like 2 days and you might get like 6 seconds worth of simulation. So the challenging thing is like, how do we scale this up so that we get on the time scales of like, this growth and remodeling? And that's something that's, has a lot of clinical interest, because, a lot of clinicians, they look at this technology and they say, okay, that's great that you can simulate like 5 seconds of heart flow, but I'm interested in saying, how can I treat this patient over the next 3 months? And right now, like the technology is just not there, but there's a lot of research that's going into it right now for sure.
That's like something we're waiting for quantum computing to be able to do stuff like that.
Yeah, for sure. Yeah, the limiting factor is definitely on the computing and just the memory too. Yeah, for sure. Any other questions on this stuff?
Yeah, one.
Sure.
Just from before, with the fluid structural interaction, the deformation for the solid part, the actual vein, are you just applying a systolic and diastolic right there?
So for that simulation, I'm applying kind of a time varying pressure wave. So you do have the systolic and diastolic pressures in there, but they kind of hit it over at a certain time. So I think you hit the systolic peak when the heart contracts, and then there's a period of time when the heart relaxes. And then at the end of the relaxation, then you hit kind of the diastolic pressure. And then it takes maybe a quarter of a second for the heart to pump, and then you hit the systolic again. So both the systolic and diastolic peaks are there. It occurs over like a time period of 1 second, basically. All right. Okay. So that's kind of just the technology in general. So that kind of took a bit longer than I thought, but that's okay. I think that's kind of the more interesting part. So now I kind of want to get into kind of the work that I've done. So as you can imagine, your cardiovascular system is very vast, and it consists of a ton of different blood vessels. So it's kind of impossible to simulate it all. So the blood vessels that I mostly focus on were the coronary anatomy. So your coronary blood vessels are the vessels that kind of wrap around your heart. So the reason it kind of gets that name is, coronary is kind of another word for crown. So if you kind of look at these blood vessels, they kind of form kind of like a crown that goes around your heart like that. And these vessels, because they're around your heart, are extremely important to your body. So even though your heart itself is filled with blood, the heart that's actually inside your blood, your heart muscle can't actually use that. So your heart itself is a muscle. So it's a muscle that's basically always contracting. But so just like any other muscle in your body, like your biceps and your quads and stuff like that, it needs blood vessels to basically feed it with oxygen and nutrients. So your coronary vessels are the ones that actually do that. Okay? And these are, the subject of a lot of medical research, because these are often, they often become restricted or blocked due to plaque. And that's kind of because they're very tortuous in nature. So you can see that they're not very straight. They kind of wind around the heart quite a bit. So what tends to happen is that if you have kind of plaque that's coming in, it tends to really stick to these walls, because the blood vessels are changing direction really rapidly. And and if your coronary blood vessels get blocked, this is usually kind of the #1 thing that leads to heart attack. So studying these vessels is it's of intense kind of clinical interest. Right? And just from a modeling perspective, so just for simulating the blood flow, if you actually measure the blood flow in the coronary arteries, what you'll notice is that they're out of phase. And so what I mean by that is that the majority of the blood flow often happens when the heart is actually relaxing. And so because they're actually on the heart, there's actually kind of this interesting effect. So when the heart squeezes and the pressure is high, that it actually squeezes all the blood vessels in your coronary arteries too. So that actually kind of prevents blood from actually flowing there. So it's only when the heart relaxes that these kind of constrictions go away, and then blood flow can actually go into your coronary arteries. So you have kind of this out of phase behavior. And so actually from a simulation perspective, this is actually really challenging to do because you basically have, your pressure's going up at one point, but then while your pressure's going down, then your flow has to go up in the coronary. So, having this kind of phase lag in between the two is a bit challenging. Okay, and so this is kind of the model that I generally use. So this kind of combines a lot of what we talked about for the boundary conditions. So I have here my 3-dimensional model. So here I'm solving the Navier-Stokes equations like we talked about. And you can see at all the inlets and outlets, what I have here are those lump parameter representations. So I have basically circuit elements to measure, to kind of represent kind of the viscous friction and the capacitance of all the vessels that are downstream. Okay. So from here, I kind of want to talk about 2 projects. So I probably only have time for one of them, but we'll try to get through it. And these are kind of 2 projects that I tackled when I was in grad school. So the first one that I'm going to talk about is tuning of the boundary conditions. And the second one that I'm going to talk about kind of corresponds to kind of the deformable wall simulations, or the fluid structure interaction. Okay. So let's talk about boundary conditions again. So what I have right here are 2 simulations that I've run. So you can kind of see from both of them the geometry is exactly the same. So it's kind of the same model that I've been kind of showing through here. And what I'm showing you here are kind of the pressure contours, or the distribution of pressures throughout the model. So what I'm showing you here is that even though the geometries are still the same, on the left right here you have a model that's relatively low pressure. So you can see the colors are kind of turquoise or blue. So what this is showing is that this person has an average blood pressure of around 92. So this is actually a pretty healthy person. So this is something that, if a doctor kind of saw someone with an average pressure of 92, then they say, you're in pretty good shape. That's pretty close to the ideal blood pressure of 120/80. So, you don't have to take any measurement. You can go home, just keep doing what you're doing. Okay? But if you look at this simulation right here, even though it's the exact same geometry, you see we have very elevated blood pressure. You can see the colors here are red, which kind of indicate that the blood pressure is going to be close to almost 120. So that's 120 average. This is something that's really bad. So this is a person that would have a hypertension or high blood pressure. So if a doctor saw this, they would say, this is someone that we need to keep an eye on. This is someone that we might need to put on aspirins or something to lower this blood pressure. So what's going on? So we have two simulations here with the exact same geometries, but the results are completely different. So on the left, we have a healthy dude, and on the right, we have a unhealthy dude. Okay? And so if the geometries are exactly the same, what's the difference in between the two? because in both cases we're solving the Navier-Stokes equations, so the governing equations are the same, but what's different in between these two are the boundary conditions. Okay? And so, you know, this kind of highlights the fact that, you know, when we're choosing the boundary conditions for our simulations, we want to choose them, you know, kind of smartly, right? And kind of remember the, you know, the kind of the phrase that I kind of talked to you before, which was patient specific, right? So we basically want these simulations to represent the physiology in the patient as closely as possible. Okay? And so what does that really mean? And so what that means is that we want to basically match things, match any other data that we know about the patient. Okay? So if you've gone to the doctor, you'll know that, you know, they measure things like your blood pressure. So they measure your maximum minimum blood pressure, or your systolic and diastolic blood pressure. We can also measure things called your stroke volume. So that's the amount of blood that your heart kind of expels in one beat. Okay, so that's something that's really important. We can also measure your ejection fraction. So ejection fraction is a big kind of indicator of health. So that's the fraction of blood that kind of leaves your heart in each beat. Okay, because when your heart kind of pumps, not all of it leaves your heart chamber. So some of it gets stuck behind. So the ejection fraction is kind of the fraction of blood that kind of gets out. Okay. So normally you want kind of a high fraction, but, you know, for unhealthy people, the ejection fraction might be as low as like 30 or 40%. Okay. And we can also measure things according to the valves. Okay. And so what we want for our simulation is not only do we want the geometry to match the patient, but we also want to kind of match these kind of physiological data, you know, exactly too. Okay. And so not only do we have patient-specific data, we also have some data that's been collected from the literature. So a lot of this data is kind of old data because that was from a time when it was morally or ethically more accepting to kind of stick probes in random people and measure stuff. So now it's a bit more difficult to do that. But, you know, because of those ethically challenging times, we have a lot of great data that we can actually use to tune our simulations to. So we want to basically make sure that we match both the patient-specific data and the literature data as close as we can. So how do we do this in practice? So, you know, the way that we do this in practice is I call this kind of this process tuning. Okay? So tuning the boundary conditions are basically choosing the values for your resistances and capacitances and flows and pressures at your inlets and outlets, such that you match your data. Okay? So there's kind of two ways you can do this. So kind of the old way to do this is called manual tuning. And so what that means is that we're basically choosing these parameters manually. So we're basically sitting at our computer and changing the values of these parameters, you know, one by one until we get the results that we want. So as you can imagine, this is extremely time consuming. It's also operator dependent. So, you know, if I change the parameters in one way, then someone else is going to change it, you know, another way. And, you know, they might get somewhat close, but, you know, they're still going to be different. Okay? If you have some kind of really skilled operators, you know, manual tuning is okay, because, you know, you can kind of benefit from the wealth of intuition that the operator has. But if you want to basically use these simulations for a large amount of patients, you know, which is eventually where we want this technology to go, because we want this technology to kind of be a tool for kind of regular clinical use, we need kind of a better way to do this. So kind of a better way to do this is through an automated method. Okay. And so the benefits of an automated method are that, you know, first of all, it's automatic. So you don't have to sit there at your computer. You can kind of tell it to go, and you can go make a sandwich for yourself or something. Another benefit is that it's going to be a lot more thorough. So you can basically search the parameter space a lot more efficiently than just someone just kind of hitting buttons at their computer. Okay? Another thing is that it can kind of, you know, very systematically encode what's called prior knowledge into your tuning. Which is kind of a lot of kind of just prior intuition that you can input in, that one person might be difficult to kind of input all that in. Okay? Another thing that it allows for, which I'm not going to get to, is uncertainty quantification, which I think kind of goes back to a question that Damien asked at the beginning, which is, you know, how do we know how reliable these simulations are? So basically an automatic tuning tool will basically allow us to kind of quantify that and give some measure of confidence in our simulation. Okay, so here's kind of some of the mathematics behind it. So this is just one very brief slide that, you know, unfortunately doesn't tell anything, but, you know, it's kind of, I had to limit this in with respect to time. So the way that we're going to do this is we're going to basically take a Bayesian approach. And so what that means is that we're basically, we have this quantity right here called the posterior. So the posterior is basically a probability distribution. So you can think of a probability distribution as like your bell curve or your Gaussian distribution. Okay. And then the way to read this is that this posterior distribution is capital P. So capital P stands for probability distribution. And this probability distribution is on your model parameters y. So y here represents all the resistances and capacitances in our boundary conditions. And then this vertical line here, what that represents is conditioned by. And so what we're saying is that this probability distribution of our model parameters is going to be, it's going to be conditioned by all the data that we have, okay? And so what we're saying is that this is going to be proportional to this quantity here, which is called your likelihood function, which basically has this functional form, and our prior distribution. So the prior distribution is kind of everything that we know about the parameters kind of beforehand. So that's kind of all of our our prior intuitive knowledge. Okay? And so, you know, we basically, what we want to do is we want to draw kind of parameter samples from this posterior distribution. And so in order to do that, you need to use a very specialized method called Markov chain Monte Carlo, or MCMC. Okay? And then once you do that, then you can basically run an optimization tool. And the tool that I use is one that's kind of pretty standard called Nelder-Mead. So this is an optimization tool that's within MATLAB. So you can run it using the function fminsearch, or it's in a lot of very popular Python packages as well. So that was kind of a very big crash course on a method that should probably take maybe like, you know, 6 or 7 or 8 slides to explain. But going into it, I think kind of detracts from kind of the theme of this talk. So I kind of just left it as just a single slide. Okay. So in order to run this method, we basically need to run our model many, many times. So if you remember, so for those in 410, remember when we did topology optimization, we basically had to, basically what ANSYS had to do was it had to run our static structural simulation, you know, hundreds and hundreds of times. So for a static structural simulation, that's not too bad to do because that can run in kind of the matter of minutes or seconds. But for a computational fluid dynamics simulation, especially one with millions of elements, you know, this is not feasible to do because it's going to take you, you know, at least, you know, 12 hours on a supercomputer in order to do that. So to actually run an optimization, it's just not practically feasible with the full CFD simulation. Okay? And so what you can do instead is you can basically replace your 3D simulation with what's called a 0D surrogate. So I basically kind of leveraged that circuit element analogy that we talked about before. And then what we can do is that instead of solving this this 3-dimensional CFD, we can solve this kind of lower order resistance surrogate, and this solves in a matter of seconds. And so what this basically allows us to do is it allows us to run kind of our really expensive MCMC or our really expensive optimization, and basically get parameter samples that we can eventually run our 3D simulation. Okay, so another big part of this project is we had to reduce the parameter space. So if I count all the parameters that went into the model, all the circuit elements, and all of the kind of extra parameters that we need, there are 37 parameters on here. So you know, if you kind of are familiar with optimization algorithms, 37 is a huge optimization problem. So that's just not practical to do. So kind of the first step to do that for this project was to actually reduce this to a set that's kind of much more tenable. And so the way that we did this was we performed sensitivity analysis. So we did both local and global sensitivity. And then through that analysis, we were able to reduce our parameter set from 37 down to 13. So 13 is kind of a much easier set of parameters to work with than 37. Okay, so before I jump into the results, I just kind of want to summarize the workflow. So the starting point for this workflow is we start with a 3-dimensional model. And so from there, we construct our resistive surrogate, because remember, we can't run our optimization or our MCMC with the full 3D model. We need to run our surrogate, okay? So the first step is to actually make sure our surrogate is actually accurate. So we enter kind of into this loop right here. So we basically run a 3D simulation and our surrogate, and then we check to see if the results match. So if they don't, then we basically improve our surrogate, but if they do, then we can move on. Okay? And then if we move on, then we run our MCMC. So we basically run our sampling algorithm for our posterior distribution. And then once we do that, we can run our optimization, and then we get our optimized parameters. Okay, and so for this particular project, I basically ran that framework for 7 different patients. So here I have 6 patients. I have six patients, I should say. So these 6 patients that I'm circling right here, what they all have in common is that they have a bypass graft. And so what that means is that they had some blockages in their coronary arteries around their heart. So they had to undergo open heart surgery to basically reroute blood kind of downstream of those vessels. And so what you can see here is you can kind of see these graphs that kind of snake through the model. So those aren't naturally there a lot of the time. So a surgeon basically went in and put that blood vessel there just so that this person can have blood that goes through their heart. And I compared that with one healthy patient. So this was kind of the first model that I made in grad school, and I kind of really got my money's worth because it kind of made its way into almost every project that I did in grad school. And so the reason I chose these patients was kind of they not only they kind of represented a nice range of different geometries, but they also represented a range of physiology too. So if you kind of compare all the different pressures and all the different stroke volumes and ejection fractions, we can see that we got a big range here. Okay? And you can see from the heart rate, we have kind of almost a double. So we have one patient that was had a heart rate of 46 beats per minute, and another patient with 88. So these were a fairly good range. And so one thing I'll comment too is that, I have 6 patients here, and don't get me wrong, this took a lot of work for me. But if you kind of show this, if you show this to kind of a medical doctor and you say that you did a medical study with only 7 patients, they will laugh at you and basically say, don't bother them ever again. So, if you kind of compare this to a lot of medical papers, and they talk about clinical trials of a new drug or something, they're talking about thousands of patients. So if you compare 7 to thousands, you can see why, the medical field kind of still looks at this technology with some skepticism. Because right now it's so labor intensive just to create one model of this, that it's really hard to kind of scale this up to get the significance that a lot of doctors really expect. So that's kind of one big kind of disconnect right now between kind of the engineering and the clinical side. Okay, so let's look at the results. So the first thing that I want to test was that, are we even hitting our targets? So first thing I checked was that, are we hitting our pressures? So here I have our systolic pressure, our diastolic pressure, the stroke volume, and the ejection fraction. Okay. So in the yellow bars here, what I'm showing here are the targets. So that's basically the result that we wanted to get from our simulation. And then in the red right here are the actual results from the simulation. Okay. And so you can see right here, all of these are matching pretty well with some exceptions. Okay. So you can see for this patient number 3, which is one of the sick patients, you can see, for the stroke volume and the systolic pressure, it struggled a little bit to reach those targets. And kind of what we expect was that, the geometry for patient 3 was very challenging. So it had a lot of different blood vessels. So let's see, I think patient 3 was, I know that these aren't in order. I think patient 3 was this one right here. So patient 3 kind of had a lot of crazy stuff going on. So it was not only did he have a lot of different graphs, but he had a lot of different, kind of disease in his arteries too. And we think that kind of extreme state of disease was kind of throwing off our simulations quite a bit. But you can see for all the other 6 patients, we were matching within the targets. We were matching their targets kind of within their bands of uncertainty here. So we were very happy with that. Okay. And so the other thing that we looked at was the coronary waveform. So if you remember what I mentioned was that, for coronary simulations, we want to capture this out of phase behavior as closely as we can. And if we measured the flow waveforms at our outlets for our simulations, we can see that we captured that pretty well. So for the left coronary waveform, we have this kind of out of phase behavior where the majority of the flow happens there. And we have kind of a small peak here. And in the right coronary waveform, the right coronaries are a little bit different because they rest on the right side of the heart. So the right side of the heart, it doesn't pump as hard as the left side. So you don't have kind of this this suppressed peak. So what generally is expected for the right coronary waveform is actually you have kind of this double peak behavior. So you have one peak that happens in systole, and then you have another peak that happens in diastole. So from our simulations, we were able to get that basically across our patients. So we're basically pretty happy with that. Okay, so just kind of the summary of this project. So basically, we basically want to run patient-specific simulations. And kind of we recognize that kind of a big step towards this is to actually tune our boundary conditions such that we match our data as closely as we can. And so the goal of this project was to develop an automated framework to tune these boundary conditions so that we match the data as close as we can. Okay? And so the way that we did this was we sampled from the posterior distribution using a Markov chain Monte Carlo method. So it's a Bayesian style method. And then when we tested this on 7 different patients, we found that we hit our targets within at least within their specified uncertainty. Okay. So I had one more project that I have in the slides. So we have 5 minutes left, so I don't think I'll have enough time to go to it. So I think I'll stop my presentation here, and if you guys have any more questions, I'll be happy to take them for the last 5 minutes. So John, oh, go ahead.
I was gonna say, so the medical field, when they do those clinical trials of drugs, aren't those usually testing like kind of surface level exterior effects more than really in-depth detailed things of what's going on internally? And
yeah.
And so, I mean, I get that they could get good statistical results, but do they not generally, is there not a lot of value in them seeing really like detailed simulations? Or is it just that there's a lot of like, they're just used to seeing high numbers of test subjects, and that's the reason that they don't value it?
Yeah, so it's kind of a couple of things. So I guess addressing your first question, you know, a lot of times when they do these clinical trials, they're testing a specific drug for a specific disease. So kind of drawing from current events right now, like once a cure for coronavirus happens, you know, and they kind of tested it, you know, amongst a lot of people, they want to see if coronavirus is going to be cured, and they can measure that, you know, with pretty good confidence. So yeah, they're not looking at kind of the very specific kind of you know, shear stress and this they're not looking at the amount of detail that you get from the simulations. But just for their goals of, you know, they want to treat this disease or they want to develop a vaccine for this, you know, they can measure that, you know, pretty accurately. So that's mostly kind of what they're interested in. And to kind of address your second question, it's not just the numbers thing, but, you know, it's kind of, you know, from the result that, you know, every human is very different, and kind of the variation of, you know, not only their cardiovascular system, but, you know, just, you know, their hormones and kind of everything about them is so different that, you know, if you know, even within our class, right, if I took, you know, 7 random people in our class, you know, it's kind of it's a stretch to say that those 7 people are kind of a representation of our class of, you know, 40 or 50, right? So if you're going to develop something that's going to be, you know, be used by the general population, which is, you know, millions, billions of people, you want to do more than just 7 people, because, you know, you want this to kind of be effective for more people. So it's kind of the question of, you know, how generalizable is this going to be?
I guess that kind of leads to another thing, like when we were talking about applications and companies that have this as a part of their business, and they hire engineers to do simulations like this. I mean, if they're going to design like maybe a heart thing or something that's going to go into like the bloodstream or something like that, how are they able to justify that off of simulations where they're not getting a bunch of test stuff from other people? Like, I mean, I guess there's parts of the body that might be more generalized, like people might have all of a standard thing, but at the same time, that thing might affect a lot of people if that's the case, where like everybody's different to the point where the medical community won't take that opinion seriously if it's only 7 different people.
Mm-hmm.
I guess there's a disconnect where I'm wondering how that businesses even survive based off of simulations like this when the numbers of subjects are so low compared to what the medical field would want.
Right. Yeah. So it's just one piece of the puzzle. So it's you know, I think we're at a state where we're not saying that simulations can replace anything that they're doing in the clinic, but it can be just one piece of the puzzle that can kind of help out. So if you kind of think about, you know, the medical field has kind of advanced up to kind of, you know, within up to like a few years ago, you know, before simulation. So, you know, it kind of shows that you can develop a lot of these things, you know, without these simulations. But what we're hoping is that these simulations can kind of provide some more insights and some more information that kind of, you know, fill in maybe some missing pieces that clinicians might not have. And then from there, we can kind of, together with a lot of their other methods, kind of improve kind of quality of care and develop new treatments. So this is kind of just one tool and just one piece of the puzzle for kind of the greater question of like, you know, overall health.
Okay, thank you.
Mm-hmm. All right, any other questions?
I just have one. Is there any reason why is this applicable to more than humans? Is it applicable to all animals with, you know, hearts and pulmonary systems and stuff like that?
Oh yeah, absolutely. Yeah, that's a great question. So there's definitely a lot of academic research in simulating, you know, animal cardiovascular systems too. And that's actually has a lot of value too, because before a lot of drugs are tested in humans, a lot of times they go into animal testing, and just as simulations, we can better understand the human cardiovascular system. We can use it to better understand animals too. So there's definitely a lot of interest and a lot of value for that as well. The difficult thing is the imaging. So humans are relatively decently sized. So our blood vessels, we can kind of easily see it on a CT scan. But if you put like a rat or like a cat into a CT scan, their blood vessels are so small that it's kind of hard to pick them up. And then kind of on the flip side, if you use a bigger animal like an elephant or something, there's no CT scan that's big enough to fit an elephant right now too. So that's kind of it's the challenge of size. So like it's easy to ask like Siemens to basically develop a machine for humans, but it's a hard sell to ask Siemens, like, can you make a CT scanner for elephants? And they might look at you kind of funny unless you have like $500 billion to throw at them. All right. Any other questions?
I know we're out of time and I don't want to keep people here. I'm really curious about this analogy between fluid mechanics and electric circuits.
Mm-hmm.
Is it possible to explain that in less than a minute, or is that something that we should discuss offline?
Yeah, I mean, I guess kind of the full answer we should definitely discuss offline, but kind of the general thing is that, I guess the way that people view circuits is that we have kind of charge or current that's kind of flowing around into a circuit. So kind of in a simple way, we think of kind of fluid that's kind of going around in a closed circuit like that. And so I think kind of the analogy is pipe flow. So when you have fluid that's going in a pipe and you have kind of a straight segment of pipe, you can kind of replace that with some kind of circuit element to kind of represent certain things. So different circuit elements kind of represent different things. So the main one is the resistor. So what the resistor kind of represents is kind of viscous stresses or viscous losses. Because when you have kind of current that flows through a resistor, you have some of that energy get dissipated as heat as it goes through the resistor. So kind of the same thing happens for fluid flow. If you have a fluid that goes through a pipe, you lose some kind of energy or kinetic energy due to basically viscous friction. And a capacitor will basically model something else, an inductor will something else. But yeah, definitely we can talk more about it offline.
Okay, thanks.
Mm-hmm. Okay, so I think we're out of time. So I want to thank everyone for coming. So I know I didn't get through everything, but I think, John, I'll send you my lecture slides. So if you want, you can forward that to your class. And I also kind of want to take, since for 417, I think this is the last time that we'll see each other, at least all together like this. For those of you that left, I just want to take a moment just to thank you guys for the semester. I know this semester was extremely challenging with COVID-19 and the lockdown and everything. And I just want to say I really appreciate you guys, working hard and still trying to make this class, try to make the best of it as we can. So I know it wasn't perfect. I know things are really difficult, but thank you guys for everything that you've done. That's all I kind of want to say.
And thank you, Dr. Tran. This was fascinating, and I speak for myself and all of my students in 430 when I say thank you very much for showing us your research today.
Yeah, of course. Yeah, thanks for having me.
Yes, thank you.
Yeah, that was awesome.
Yeah, thank you guys.
Thank you.
Yep.
Take care.
Thanks, you too. All right, bye everybody.
Bye.
Bye.